Hey guys, welcome to the channel. Today we're going to be doing a small signal analysis of the common base emitter. This is the configuration they have in the Microelectronics 7th edition, and I highly suggest that textbook if you want to learn about electronics. So, important thing to note, how do we know if it's a common base emitter? Well, what we see here is we have the voltage output, V0, attached to the collector while the input is connected to the emitter. That leaves the base, which is the leftmost segment of the transistor. This does not have an input or output. That's how we determine. So say the input was here in the base and the output was in the collector, we'd have a common emitter. And just an important few key things to note. Whichever way the arrow is pointing will determine whether it's an NPN or PNP. If the arrow is pointing out of the transistor, it's an NPN, but if it's pointing inwards, then it's a PNP. And the emitter is always going to be the segment with the arrow, just to keep you guys on track. So over to the right hand side, we have our NPN and PNP equivalent pi models right here. So as you can see for the NPN and the PNP, the base is always connected to the left, while the emitter is always at the bottom. The collector is always at the right. And we can see for the NPN, the current is flowing downwards in each segment, the base, collector, and emitter. But in the PNP, the current is clearly flowing upwards. That's the big difference of the PNP and NPN. There's also a DC analysis difference, which I will cover in a different video. Also important to note, there are many other models that you can use, like the T model. There's other hybrid pi models, but I find this one to be the easiest. And you guys can do whichever one, you'll still get the same results. So what are we going to derive today? We're going to find the voltage gain, V0 over Vn, the input resistance, the overall voltage gain, and the output resistance. So first, we obviously have to make our circuit into the AC domain. So how do we do that? We have to short circuit all the capacitors. We have to ground all the DC sources. Alright, so what our circuit is going to look like. So remember, my first tip to drawing these is always to draw the model first. So here we have, remember, it's an NPN, so the currents will flow in a downwards fashion. And the current source, beta IB. There. So now that we've drawn this, we want to kind of draw it one piece at a time. So let's take the base, for example. The base is really easy. We see that it's simply just connected to ground. Now for the emitter, we have a current source going down. But remember, we have to deactivate all DC sources. And how do we deactivate a DC current source? We have to open circuit it. And then for the VEE, that will also have to be grounded because that is a DC voltage source. And then, remember, short circuit the capacitor. And then we have our voltage input connected to the ground, our signal resistance, and our signal voltage also connected to the ground. So now we've done 2 out of 3. We also have to just do the collector. We see RL, and then the final one, RC, which we will have to connect to ground because VCC is always the DC source. Now, quickly, what we can notice is RC is in parallel with RL, so we can get rid of that. This becomes RC in parallel with RL, with V naught being attached here. So now that we have our equivalent model, we can start finding our equations. So first, let's start off with the voltage gain, V naught over Vin. So here what we're going to have to do, we have to find equations for Vout and Vin. We want to find these only in terms of resistance and DC parameters, so like beta, R pi, and etc. So from here, what we can see, let's find Vout first. Vout, it has one current going through it, that's beta IB. And we know that the voltage is current multiplied by resistance. So V naught here is clearly equal to beta IB multiplied by RC in parallel with RL. But wait, we're not done yet, because we notice that the V out is not following the passive convention with the current source. So that means we have to make this a negative. Now for the V in, we see we can't really just find any easy equations just like how we did here. What we have to do is KVL or KCL. In here, it's really simple, guys. We can just do a simple KVL around this loop. And performing the KVL there gives us, we have, starting from this node right here, we can say V in equals negative R pi IB. So now that we have two equations, we can say V naught over V in equals negative beta IB RC in parallel with RL divided by negative R pi IB. Now, what's really important to note here, that the currents will cancel out, the negatives will cancel out, and we're simply left with beta R. Oh, whoops. Let's erase that. Beta RC in parallel with RL over R pi. So this right here is going to be our voltage gain. So for the input resistance, what we're doing is we're finding the equivalent resistance through the eyes of the voltage in terminal. So that means we're finding the equivalent resistance of this circuit here. Alright, so let's go back. So how do we do that? There's multiple ways to find Thevenin equivalent resistance, but the easiest one in this case would be to add the 1 amp current source and find the voltage across here. So what we're gonna be adding that shortly, but it's also important to note that when you add a DC source, you have to deactivate the AC source. So that means the AC components will be removed from the circuit, and we'll redraw this terminal as a 1 amp current source with a voltage VT across it. So now that we have our new circuit that we're going to derive R in from, we can clearly see that IE is supposed to be flowing downwards, but the 1 amp kind of contradicts that. So we can write this as 1 equals negative IE. And now we want to find an equation that can help us find VT. The easiest one here would simply be a KVL from this node all the way to here. So from here, what we get, KVL, we see that VT plus R pi IB equals 0. So VT equals negative R pi IB. And from this equation, let's write this in green, we know that IE equals beta plus 1 IB. So we can turn this into 1 equals negative beta plus 1 IB and turn IB into negative 1 over beta plus 1. So now that we have an equation for IB here, we can bring it over to VT. So what we get from this is VT equals negative R pi multiplied by negative 1 over beta plus 1. Now we can see that the negatives cancel out, and we get R pi over beta plus 1. Now this will be our input resistance right here. Now to find the overall voltage gain, it is going to be we'll just write it here, equals V naught over V sig. Now another way we can write this is V naught over V sig multiplied by V in over V in, since this is technically just multiplying both sides by 1. So our voltage gain overall becomes V naught over V in times V in over V sig. Now this makes it a lot easier because we've already found our voltage gain from earlier, and V in over V sig is a very simple computation. Simply, since we found the Thevenin equivalent resistance, we now know a very simplified circuit Remember, we can do this because we found the Thevenin equivalence resistance for everything else that's connected to V sig and R sig. So what we can do here, a simple voltage divider will do the trick. V in equals V sig R in over R sig plus R in. So V in over V sig, if we just divide both sides by V sig, we get R in over, we get R in over R sig plus R in. So now we can see that our overall voltage gain will be the voltage gain we found from earlier multiplied by R in over R sig plus R in. And these are all stuff that we've rather given, which in R sig will be given, and R in we computed that just a couple seconds or minutes ago, and AV we computed at the beginning of the video. So this will be your overall voltage gain. So for our output voltage or output resistance, we're going to be doing something similar to the input resistance. We have to find a Thevenin. So how are we going to do that? Again, we're just going to add a 1 amp current source and find the voltage across it. Now, simply, so here we can replace RL with this current source. And it's also important to note that you might think that you have to replace RC in parallel with RL, but that's just because we combine it in parallel. The actual terminal is only across the RL resistance. So that's why we can only replace this resistance here and not the RC. So what we'll do is simply just draw a 1 amp current source. We'll call the voltage VT again, and we have to find VT. So simply what we can do, this probably the most obvious case right now, is a KCL at the node A that I labeled. We'll do that in green. So we see that 1 equals VT over RC. Now we know that VT is going to be the current at A, which will be the current flowing through RC. That's why it's VT over RC plus beta IB. Now clearly here we have to find a function of IB. Also, do not forget to remove the AC component. I completely forgot about that. I'm sorry. Now, what we can quickly notice is, since we do not have an input anymore in the emitter, we can clearly see that here's an open circuit right here. So that means we have no current flowing through the emitter. So that means IB is equal to IE over beta plus 1. Clearly here, IB is going to be equal to 0. So that means IC, which is beta IB, will also be equal to 0. So essentially, the circuit that we have remaining will be like this. And from here we can easily find that the voltage is simply going to be RC, since V equals IR, and we know that the current's obviously equal to 1, so we see that V of T equals RC. And remember, since R out is going to be VT multiplied by 1, R out is simply just RC. Thank you guys for watching, and I hope you learned something.